For our experiment, we'll be studying how a bike tire reacts to changes in temperature and relating that to the pressure inside the tire. We will be measuring the temperature with this thermometer and measuring the pressure with this bike pump, which has a gauge on it. Some assumptions we made are that the bike tire frame keeps the tube as a rigid body, and because of that, we assume that for our initial calculations that this is an ideal gas. For our initial conditions, we found that the temperature was 70 degrees Fahrenheit and that the pressure inside the tube was at 2 bar. We later converted these to metric units.
Starting off, we'll partially submerge the wheel in ice water and leave it in for 20 minutes so that the tire has time to cool down. Once 20 minutes have passed, we'll pull the tire out and get a temperature reading of the water and assume that it represents the internal temperature. We will also read the pressure reading of the tire using a bike pump gauge. A couple of factors that would affect the accuracy of this experiment in this case would be the entire tire not being submerged in the water due to the space available. The time given most likely didn't allow for a full heat transfer, thus the relationship might be slightly disproportionate to the theoretical results, and the possibility slight pressure leakage due to the pump used and the valve on the tire.
So we'll go ahead. Alright, so we're going to go ahead and take the pressure and the temperature reading after 20 minutes in the bathtub with ice. After that, it dropped to about 1.5 bars. And then, looking at trying to angle it, yeah. And then our temperature reading was about 62 over the final temperature.
This process will then be repeated again, but in hot water this time, in order to provide analysis for the opposite end of the temperature spectrum. The overall relationship between pressure and temperature can be more accurately discovered after the heat measurements are also taken. The temperature of the water drops slightly throughout the duration of the 20 minutes due to the water transferring some heat to the atmosphere.
The tub after 20 minutes, and the pressure was about 2.5 to 3 bar, though we did accidentally let out a tiny bit of air on the tire to check it. But yeah, temperature was about 115 degrees Fahrenheit, so it was definitely hot.
The data provided on the tire itself, we reflected that the volume of the tire tube is 0.00261 meters cubed, and then using the mass of air, we calculated that the mass of air inside the tire is this value shown here. Now, going over here, we assume that it is an ideal gas, and our assumption is that the pressure divided by the temperature is equal to the pressure divided by the temperature at a different state. We took our initial state, which is 7 degrees Fahrenheit, but we converted it to Celsius here, so that's the 21, and our initial temperature, our initial pressure from bars, we converted it into the absolute pressure in kPa, and then from there, we were able to calculate, based off of a guessed internal temperature, a new pressure based off of that, using our assumption that P1 over a temperature equals the pressure over another temperature. So, after collecting all of our results, we compiled them into an Excel file here. We took our temperature measured in Fahrenheit, converted to Celsius, and our gauge pressure, and we converted that into absolute pressure in kPa. Assuming that it's rigid body, volume and specific volume should remain unchanged in this scenario. So after collecting all the data, we converted it from Fahrenheit into Celsius, and we converted our gauge pressure into absolute pressure in kPa. From there, we use the ideal gas law to calculate the specific volume, and then calculate the regular volume. To help prove our conditions, we assumed that it wasn't a rigid body in this scenario, and that we calculated our reduced pressure by using the critical pressure and critical temperature to help calculate our reduced temperature. From there, we use the generalized compressibility chart from here. Looking at a reduced pressure, it's a very low number, less than half, which would, on the compressibility chart, we put it right up against this line. Looking at reduced temperature, it's about between 2.1 and 2.4, which is this, a little bit above this line, right over there. All of our values are about in this area. For our compressibility factors, some are between 0.98 and 0.999. Using these values, I was actually able to calculate that our initial volume was correct by using this initial values of compressibility shown here. This is volume is calculated by taking our specific volume and kept multiplying it by an initial mass.
Because our general compressibility factor is close to 1, the ideal gas assumption remains the same. However, due to the shortcomings of the experiment, the calculated values will not be exact, but they will have the same concepts